This is the 11th video recording in a class on single agent search, and we are now a couple lectures into looking at suboptimal search. And what we're going to be looking at today is what happens with weighted A star when we allow node re-expansions. So in the previous parts of the lecture on suboptimal search, we've looked at how many algorithms require that A star, or the suboptimal search algorithm being used, is required to re-expand nodes. And this is done primarily to maintain an F-min, which is known to have an optimal F cost. And that allows us to do proofs for our solutions fairly easily. That our solutions, when we find a more expensive solution, we use that lower bound to prove it. But this can cause problems. And so we're going to show some of those problems, and we're going to show some of the other weaknesses of weighted A star in this lecture. And then when we're done with that, we'll start to look at how we can avoid doing re-expansions. And so we're going to start by looking at a case here where weighted A star can actually do a polynomial number of re-expansions. So in this particular example, this is a generic example that we could build for any weight. We can create this exact same behavior by adjusting the weights that are here on the edges. And you can also play with this online. There's a demo for this that allows you to see this behavior, but we're just going to step through here and watch what happens and try and understand what happens. The other thing to understand is that this example is, in some senses, contrived. I've carefully configured the weights here to cause the problems that I'm talking about, but this is only because we want to create a very simple example that can very easily be scaled. In real-world examples where we solve in like a grid world or something like this, we can create the same sort of behavior fairly easily. And so this is just sort of the extreme version that's going to make it, it's going to make it very obvious to see what's going on here, or I hope it's going to be obvious. And so what we have in this problem is we have a start state, which is up here. Actually, I'm going to use this to highlight this. So we have a start state up here. We have a goal state down there, and we'd like to find the path. And there's actually only one path to get here, which is going right here. And then what we have is we have two paths that are sort of heading to the right, and along these paths, the edge costs are all 1. Okay, and then we see the heuristic 4, 3, 2, 1, 0, 4, 3, 2, 1, 0, and then 5, there's an edge cost of 5, and we go to 0 here. So that's fairly straightforward. The only complication that we have here is that these edge costs, so they start small, 0.67, 0.33, 2.0, 2.67, 3.33. So these edge costs are going up, and we could be putting multiple nodes inside here. This might be one edge, but this might be 2 edges of cost 2/3, 3 edges of cost 2/3. But just for simplicity, we're going to increase the edge cost across here. And what we're going to do is we're going to watch at what happens. So as a reminder, this is the H cost here. These are the edge costs. And what we're just going to do is we're going to start looking at what is the F cost of nodes. So what is the behavior of weighted A star going to be? And to be clear, we're going to run weighted A star. We're going to simulate weighted A star with a weight is equal to 3. Okay, so this is going to be a little bit detailed here, but we're just trying to understand what's going on in this behavior. And then we'll watch this run on a larger problem instance more quickly to understand it. Okay, so to start out, we're going to expand the start state here. We're going to generate 2 successors. And when we generate these 2 successors, we're going to generate them with a F cost. And so the F cost, remember, is G plus H. So I'm going to write the F cost in here in blue. The G cost is 1. W times H. The H cost is 9. So 3, the weight of 3 up here, times the heuristic of 3. Gives us 9 plus 1 is 10. So that's the F cost for that state. Down here, we have 3 times 4 is 12. So again, our weight is 3. Our heuristic is 4. 3 times 4 is 12. Plus the edge cost gives us 12.67 as the cost for that node. Okay. And because weighted A star, like any best first search, is going to be choosing the best node to expand next, we're now going to choose to expand this node. So we'll mark that there. So that node's going to be expanded. We're going to generate its 2 children. So now we have T2 on the top. T2 has a G cost of 2. And So we'll just write that down, plus, and h times w, so g plus w times h is 3 times 2 is 6, is equal to 8. So that's the cost of that node. And if we think about coming down this edge here from this node, so right, we've expanded here. This is on the open list. We're putting that on the open list, and then we're considering this path. So we have a cost of 2.33 plus w times h, 3 times 3 is 9, is equal to 11.33. Okay, so that's the F cost of B1. So these are labeled T on the top and B on the bottom. Okay, so we look at this and we're now going to choose the minimum, 12.67, 11.33, and then 8. So we're going to choose to expand this node with cost 8 next. And now we're going to continue to generate. So now we've got cost 1, 2, 3. So that's 3 plus w times 1 is 3. This is going to have a priority of 6 here. And on the bottom here, in B2, we're going to generate a cost of 1, 2, 3, 4. Just to be clear, that's 1, 2, 3, 4 is the path to get here, plus w 3 times 2 is 6. The priority of this state is 10. Okay, so what we see here is we're going to continue to go across the top here because it has lower priority. And the reason why is that the edge costs from the top to the bottom, so basically the costs going across the bottom are all, once we go down onto the bottom, the costs are all the same. But since going down to the bottom is a little bit more expensive than going to the right, then we're going to continue to go to the right. Okay, so we're expanding here, and now we're going to be looking at these two paths right there. So here we've got a G cost of 1, 2, 3, 4, and an H cost of 0. So here we have a cost of priority of 4. And then we have 1, 2, 3, 4, 5.67 plus, so that's 1, 2, 3, 4, 5, 6.67 plus 1 times 3 is 3 is equal to 8.67. Okay. And therefore, we're going to now choose to expand the node on the top. The 4 here will generate its child, which is going to be 1, 2, 3, 4, 5, 6, 7 and a third. And the heuristic is 0, so 7.33 is the priority of that state. And now what we're going to do is we're going to expand this state. Okay. This state here does not give us a shorter path to any other state. And so we are, so we've expanded that and we're done. We're now going to expand the next best cost on the open list. So far it's fairly straightforward. We've gone straight across here and now we've gone down here. And where it's going to get interesting is now we're thinking about this path here. And what we're going to discover is that this path is actually shorter than this path. And because we're using re-expansion policy, then once I've taken this path, I'm now going to expand the shorter path to here. And in general, we'll keep doing this. And we'll come here. Okay. So let's watch this happen. So here we have 7.33. Sorry, we had that before. But now what's going to happen is we're going to expand this 8.67. So we choose to expand that. There, we've done that. And what we're going to discover actually is that now we have a path which is 1, 2, 3, 4, 5, 6.67, which is shorter than the 7.33. So we cross this off. So cross this off, and we're going to get 7.67. 1, 2, 3, 4, 5, 6. Sorry, did I do that wrong? 1, 2, 3, 4, 5, 6. Sorry, so that should be 6.67. And that's going to be a shorter path to this state. So we're going to put it back onto the open list. And at that point, because I have a shorter path, and it's the lowest cost everywhere, I'm going to now choose to expand that. Now, the next best node on the open list is the 10 here. So I'm going to expand that next. And so what happens here when I expand that? Well, I find a path, 1, 2, 3, 4, 5, to B3, which is shorter than the 5.67 I had before. So now I say I found a path here, cost 5, plus 3 for the heuristic, and we found a priority of 8. And since 8 is lower than every other state, I'm going to expand 8. So I'm going to do that a second time. And when I do that, now I'm going to find a shorter path. So 5, I'm going to now find a path called 6. That was 6.67. This is going to be 6.0 to this node. And then I will take this bottom node and I will generate it again with a lower cost. And then because it'll be lowest, I'll go ahead and expand it. And I'm not going to continue the full process here, but this, what you can see here is we'll expand this node again, and then we'll find a shorter path here, a shorter path here, and a shorter path here. And then we'll expand this node, finding a shorter path here, a shorter path here, a shorter path here, and then a shorter path there. And then finally, we'll expand this state and we'll go to the goal. And if we look at this problem and we see what's happening, what we see is that along this piece down here, so this is the piece that's causing us trouble, and I'll do this in a different color. So what we're going to see is the first node, we have 1 expansion. The second node is going to be expanded 2 times. The third one will be expanded 3 times, and then 1, 2, 3, 4 is 4 times, and 1, 2, 3, 4, 5 we expand it 5 times. And what we see here is that the number of nodes, we have 1, 2, 3, 4, 5 nodes. The total number of nodes in the graph, if we call that n, then the total nodes in the graph is 2 times n plus 2, because we have n nodes here, we have n nodes here, and then we have 2 nodes here. And so we can scale this problem by increasing n, the number of nodes at this level, 5, 6, 7, 8, 9, 10, and we can get the exact same behavior. And what we see is that this node here will be expanded not just 5 times, but in general, it'll be expanded n times. And what we'll see in this bottom row is that we'll get 1 plus 2 plus 3 plus ... plus n, which is equal to n times n plus 1 over 2, which is bounded by n squared. Okay, so the total number of nodes in the graph is O of n. The number of expansions that occur in the graph is O of n squared. And therefore, by using weighted A star and performing re-expansions, we can take a graph with n nodes, and instead of doing something less than that, which is what we're hoping would happen, we can actually do n squared expansions, which is going to be far worse in practice. And just to show this, here's an example. And we can watch this run. So we see it go all the way across, and then on the bottom, we're going back and forth and back and forth and back and forth and back and forth. Every single time we go all the way across to the right, and then we finally find the shortest path on the bottom. And so this just shows that weighted A star, if we choose to do re-expansions, can have bad behavior. Now, this isn't necessarily the worst case behavior. Weighted A star is related to A star with inconsistent heuristics, and so I suspect, although I haven't proven it, that the worst case for weighted A star actually could be exponential, and that's just something that hasn't been written down. But so that's an open question that one of my graduate students is working on. Maybe by the time this video, if you're watching this video after I'm teaching this class, he may have resolved that already. But I think the important point here is to understand is that re-expansions can be very expensive. And as we in fact, as we look back into IDA star, we saw that IDA star had problems with re-expansions, because if IDA star didn't grow fast enough in the trees, we saw the same n squared behavior in IDA star. And we're going to see with inconsistent heuristics, we're also going to see behavior where we can get this n squared overhead in doing too many re-expansions. So that's important to understand, because it's going to motivate the question of how can we avoid doing re-expansions, and that's going to give us very simple alternate variants of weighted A star that are also performant. I want to then also show, for the second part of this lecture, is I'd like to show one of the things. Let's go back into our slides here. And what I'd like to show is another property of weighted A star. And this may be a little bit surprising, or maybe it's not, but it ends up that weighted A star, weighted A star, it finds W optimal solutions. Or we know they're no more than W times the optimal solution. But although that is the case, there do exist problems where there are W suboptimal solutions that W weighted A star is unable to find. And the reason for this is that weighted A star actually is trying to distribute its suboptimality very evenly across the paths that it finds. And so when the suboptimality isn't evenly distributed, weighted A star may have trouble using the suboptimality. And let me explain that to you. So we're going to use a very simple example from a paper that we published a while back. And the problem is going to look like this. So I'm going to have the start here. I'm going to have some path here that is going to go to a middle state here. And then I'm going to have some path here that's going to go to the goal. And here we're going to say 90 is the edge, is that edge, which might be multiple nodes. And then 100 is this edge, which again could be multiple nodes. And then we're going to have a suboptimal path. And what we're going to do is so we're going to have a suboptimal path that we would like to find, which goes to n with cost 100, and then it goes to g with cost 240. So what we know here is that C star, the optimal solution cost, is equal to 190, and we have this alternate path, and the alternate path has cost 340. Okay. And so we might try and search, right? If I use W is equal to 2, then what we'd see is that twice the optimal solution here would be 380. 380 would be W optimal. Okay. And so this solution here on the top is 340. So the question would be, well, can weighted A star go ahead and find that solution? And the answer is actually no. And what we see here, if we're trying to analyze what's happening, is that when we find this edge from S to N here, we basically allow this edge, which is cost 90, we can allow some suboptimality upon that edge. And here we've actually only had a suboptimality of 10, where we were allowed to be having a suboptimality of 90. Like we could have actually had a path of 180 here. And similarly here, then, we're going to find an edge. There is an edge of cost 100 here. And there is a path of 240. And what we would see is basically that this path is more than twice the cost of this path down here. And so weighted A star isn't allowed actually to find this path. Okay, so what we can look at here is if we were to just think about this, like what is happening here. Well, when I get to n, I find a cost of solution 100. But if I got to n and then I wanted to expand the goal, what I would have is the f cost of that path would be the g cost, which would be 340. And then we have the heuristic, which is 0 at the goal. And so that would be the f cost of that state. But if we think about some path, some node here, which is either along this path, or somewhere along one of these paths on the bottom, we could ask, is it ever possible to have can we put a priority of 340 on there? So if we look just for instance at f of n, what is f of n equal to? If I were to find the optimal solution, then f of n, or if I was to be finding it, and sorry, we're going to put h is equal to 100 here. So we know that the solution is 100 here, or because we can see the heuristic is 100, we find a path of 100. We actually know that's optimal. If we look at f of n, well, it's either 90 or 100. Let's just say it's 100 plus 2 times 100. Then the f cost there would be 300. And now when I look at going directly to g, f of g of the goal, sorry, is 340. Okay, but when we look at the nodes that are going along this path right here, so the nodes that are going along the path to the goal, then when we think about those nodes, what's going to happen there? Well, we could just choose some node. In fact, we can choose some node that's sort of arbitrarily close to the goal. So we could even put a 0 edge cost there. Think about the goal on the optimal path. And so I think about the goal, well, what's going to happen? I'm going to have cost, which is 100 plus 100. So this is going to be 200. And then the heuristic is 0. So that's going to be plus 0 is going to be have a priority of 200. So what I'm going to be forced to do when I run weighted A star on this problem is I may be able to first go right here and find this path to n very quickly and not have to expand all of some long path here that's just slightly shorter. But once I get to n, even with its direct edge to g and the heuristic of 100, I could look at this and say, well, I've gone 100, and in this particular problem, what we could say is like we could put a heuristic of 180 here. And so I can, if I analyze this problem, what I'd say is like, well, 180 doubled, even double 180 would be 360. So it feels like 340, I should just be able to accept that solution and be done. But weighted A star, with n sitting on the priority queue, any node that is along this optimal path from n to g is always going to have lower priority because it starts at 300 right here, and it's going to go down to 200 when we get sort of right next to the goal. All these nodes are going to have lower priority than actually the path right here. So even though at the high level, we actually have all the information from the starting heuristic value of 180 and from these two edges here of cost 340, so that's within 2 times of the initial heuristic. If we put that in, we'd immediately be able to terminate. Weighted A star can't do that, and weighted A star is going to be forced to go this way instead of the fewer node expansions that we could just by hopping here twice. Okay, so weighted A star basically says, look, if I'm allowed a suboptimality of 2, I'll be able to have that on some portion of this path and some portion of this path, but I can't do something like allow more suboptimality here and less suboptimality there. And so this is something else that goes on with weighted A star, and we're going to see how we can take the suboptimality and be able to shift that around to get suboptimality in different places on our path. Okay, so this is showing some of the drawbacks of weighted A star, and now what we're going to look at is what are some things that we could do to try and come up with an algorithm that maybe is going to solve both of these drawbacks. So we want to avoid doing re-expansions to avoid the worst case behavior we've seen. And then we also want to maybe be able to shift around where our path is suboptimal. And so we'll start to look at that in the next video.